Anyway, you see my nurse and my friends already back. How about you? No, but maybe you saw me today. That's what it is. Because he was I do not pretend. Yeah. It's on the case, you said. Not as
It's you can't hear it, right?
No, it was yours, so it should be in this.
No, see, it doesn't really. I wonder why.
Yeah, that's what we want.
This time it's not connecting. I don't know why.
Let's go back.
No, no, it's. I think it's. Can I do that? Right?
Yeah, sure, sure. That's the reason. Yeah, sure.
Ah, excellent. Yes. Can you say something? Can you say something? Tiberita?
Ask her what time.
Hi.
Hi.
Yes.
Okay, we can hear you perfectly. Thank you.
Yeah.
Yeah. And I'm sharing screen and we can get started. Apologies for the delay. I am, I think he's recording already.
Yes. Now I can see it. Yeah, perfect. Can you turn the lights?
Yeah. Makes it easier to see the screens.
I think this one here.
Well, that's
That good?
your own.
I don't understand.
Yeah, is there a way to remove those lights in any way?
Turn them on. I'm gonna try this other one. Turn them on.
That's okay. Yeah, do you want them off or do you want them on? I mean, I don't mind, but you're the one staring. Yeah, I think that's easier to see, no? Oh yeah, you can turn on the middle ones, like the soft top ones, no, the other ones. Yeah, no, only one of them, not two. Yes.
Okay.
Perfect. So you should be able to see some and okay. So is my mic working? Apparently, yes. Fantastic. So this morning I went over the rules of the ZX calculus in full. So instead of doing the double construction and probabilities, I actually went over the full set of rules for the ZX calculus and so the bialgebra or square popping law and the Hopf law. So I thought this afternoon I could start by giving the general version of these rules that works for arbitrary groups. So the qubit version of the calculus. So you get that the qubit version is just a special case modulo 2, which is boring, but also very useful. It has nice properties at the very least. So I think I will start with that. How is the group theory around here? Who's familiar with group theory? Who's familiar enough with group theory? Okay, mostly. Fine. So let's start with the simple case. Just a brief recap, so we're all on the same page. I'm going to treat the case of cyclic groups, finite abelian cyclic groups, because the other cases are kind of derived from those anyway. That means that we can take the algebra over a finite abelian cyclic group that has a computational basis, which is indexed by the numbers, the integers from 0 to n-1. So let's take the group of integers modulo n. And there is a second basis. So this is the computational basis. And there's a second basis, which is called the Fourier basis, which is also indexed by the integers, but it's a different set of states. I'm going to denote them with a chi or key. And this is going to be called the Fourier basis. And the Fourier basis is fairly easy to define explicitly. It's going to be the normalized version, so 1 over root n, sum k equals 0, n-1. So it has a sum of all of the computational basis states. In fact, I'm going to use a different letter just to reduce the burden, computational burden on our brains. So I'm going to try to use consistently J for the computational basis and K for the Fourier basis so that we have some, at least our brains are helped in the process. So it's a superposition of all of the computational basis states. So all of the elements, all of the integers modulo n with a phase. And this phase is e to the, okay, I'm going to write the phase as chi kj so that it becomes clear what that chi was. And chi k of j is defined to be e to the I. It has to be modulo 2 pi. So I have to somehow go from modular integers to angles. So it's going to be 2 pi. And the simplest thing I can do is just do k times j over n. Now that might sound ill-defined because these are modular integers, so you might not want to trust that this works. But if you imagine that instead of k, you take k plus n, or instead of j, you take j plus n. So this is going to be an aside for me. Take some representatives, different representatives. You get k plus an times j plus bn over n times 2 pi. This is going to be 2 pi kj over n plus 2 pi something, which is an integer, n over n. So it is equal to 2 pi kj over n modulo 2 pi, because the n and the n cancel out. So this is well defined. That it looks like it might be a bit weird, but it turns out that it's the dividing by n that makes the definition of these phases. And these are phases, right? These are all numbers in S1. What is this particular state that I defined? Well, if I think of the, and this is again, if you know your group theory and representation theory, sorry, this is going to end within the next minute or so, but just to have everybody on the same basis. This goes from my group into S1. And it has an interesting property. I can prove that if I apply it to I plus j, it's the same as applying to I, applying to j, and taking the product. It's also true that if I apply to 0, I get 1. And it's true that if I apply to minus j, I get the complex conjugate of the same function applied to j. It's why I called it chi. It is a multiplicative character of my group. So if you know representation theory, these are multiplicative characters. And the Fourier basis is just normalized multiplicative characters. As usual, I will not bother too much with the normalization factors because you can shift them left and right. There are easy ways of figuring out which things should be normalized and which things shouldn't. Here I define them normalized because typically people talk about the Fourier basis as the normalized version, but you could have taken the unnormalized states and everything works fine. So now the ZX calculus for this new setup, which is slightly more, it's more general than the original setup. I'm going to take the Z basis spiders to be defined by the computational basis. So I'm going to say Z to mean the basis of group elements, and I'm going to say X to mean the Fourier basis. So this is the general version of what the ZX calculus does. So this time, instead of being just 0 and 1, it's going to be a sum over all the numbers modulo D. So it's going to be J from 0 to n minus 1. In the case of the ZX calculus, the group is Z2, so it's J0, J equal 1, and that's it. And it works kind of the same, except it is e to the I alpha j, j dot 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 j, j dot 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 j. It's like that, where I have the bra consists of, the bra annihilates the inputs, if you will. So it has n terms, and the cat creates the outputs. So it has m terms. The little m, n, what would you like? Pick a letter. P. Yeah, that's fine.
The Jn is not the same n. No, don't leave n.
Oh,
Yeah.
you're right. I'm gonna take D. Does D work? Dimension? Sorry, I thank you. I did not even realize I had made I overloaded my notation inadvertently. 1 second, it will be fixed and you will not. Sorry?
Later on, we were going to.
Yes. Yes, yes. You are completely correct. There you go. D is nice. I should have taken P, in fact, because most of the cases that are of interest to people are prime numbers. So yeah, you're totally right. But they don't have to be, is the point I'll try to make. Yeah, up to 180 rotation. Yeah, you're right. Yeah, it's up to a change of phase. It's okay. Good. Excellent. It works out. All right. I think I replaced all of the offending ends except for this one. And now I can use my letters. Fantastic. This should be good. Now, I will take as a convention alpha of 0 to be 0. That's in order to fix a global phase so that I don't have this spurious global phase that will annoy me. It's the same as saying that this spider is the matrix which has 1, e to the I alpha 1, e to the I alpha 2, ... e to the I alpha d minus 1. So it's that matrix there. That's about it. And now I defined the X spider, which is going to be the dual spider, or the Pontryagin dual spider. I'm going to ignore the under. And it's going to be defined the same way, but using the Fourier basis instead. So it's the same definition, but where I replace all j's with chi of j's. And by the way, it is worth pointing out, and I will in a second, that my choice for chi was not the only choice you can make. This is maybe of interest to some who study this Pontryagin dual. Actually, I don't know. Is it Pontryagin? Is it Pontryagin? Is it Pontryagin? Does anybody? Pontryagin. I have no idea. In the original language, you know what the original pronunciation is? No? I mean, one wonders. So let's say Pontryagin. Okay. I'm not sure. I never really thought of it. So here's a point for the here's a point for group theory enthusiasts. There's a duality between a group, finite abelian group, and in fact, certainly a cyclic group at the very least, and what's known as its dual. So the group formed by its characters under multiplication. They are isomorphic. They're not canonically isomorphic at all. So there are many isomorphisms that you can have. The one that I picked sends J into chi of J, but I could have equally picked J into chi of Pj for any P invertible mod n. So every P in the, I should write it properly, P in Znx, so in the invertible, because it's just a reshuffling of the indices. I could have picked any of them. And this is, in the discrete case, this is kind of, why would you care about that? But in the continuous case, it's actually quite fascinating because that's a choice of, you take the same exact setup and you ask, hang on, I have the reals and I technically have the characters over the reals. And again, it so happens that the two groups are isomorphic. They are abelian Lie groups. And in this case, it's kind of interesting what the transformation is. It's a transformation that sends X into, like you could do e to the, what is it, X into the map that sends y into e to the I xy, but you could also send X into y into e to the I xy over h bar for some h bar different from 0. And that would be the same. In fact, it's a choice of unit it's a choice of units of measurement. There's a freedom to choose units of measurement in the position momentum duality. That choice is typically the h bar constant. And that choice of constant corresponds to speaking a specific duality between position and momentum. There is one way of identifying elements of the line with momenta, but technically the canonical momenta are the characters, and that identification is not a canonical one. So you have to pick one, and the choice is really just the choice of units of measurement. So it so happens that it has physical significance in quantum mechanics. So it does also in the case of the finite abelian groups. You can really think of it as a choice of units or a choice of direction, if you will. It's what it is, but for finite discrete cases. Now I have these two spiders, and I have a map. I have a Hadamard, and this Hadamard is no longer self-adjoint because it can't be, not in general, at the very least. It is going to be the map that sends each computational basis state. So it's a computational basis state and produces the corresponding character. Again, this particular choice of map depends on my duality. In fact, this is where this choice of duality comes into play. The spider, the X spider, the Fourier basis spider, doesn't depend on the choice. It's invariant under the permutation. All that happens is that you change the meaning of the phases, of the alphas. But the Hadamard is a choice of basis. It's a choice of basis, including a choice of identification between the computational basis states and the Fourier basis states. So that's where the identification happens, and its dagger, its adjoint, is going to be the dual or the inverse. I guess I don't have to define it, is a consequence of the definition above. So it's similar, but it goes from the Fourier basis to the computational basis. I'm going to pick this convention. Some people pick the opposite convention. Who cares? It works out. And now I can look at a few interesting things. Sorry, if you are taking some notes, I can pause there for a second. I'm just going to say it. We will now observe that the ZX calculus, with all of its freedom of flipping wires around, is a bit limited in this new setting, in the sense that there's a choice to be made as to which cup and cap we use. And we can pick either of the two spiders, but it is easier to think of transpose in the position basis. So in the computational basis, you imagine that you take a matrix, and this matrix, you write A, B, C, D in the computational basis, so that, for example, 0 is 1, 0, and 1 is, actually, let me take a Qtrit case, okay? A, B, C, D, E, F, G, H, K, like that. And so you have 3 computational basis states, 1, 0, 0, 0, 1, 0, and 0, 0, 1. It's just that the Qtrits are the simplest case where things go wrong. And now you want to take the transpose of this matrix, and you want to say that if I take the transpose of this matrix, I want to write it as A, B, C, D, E, F, G, H, K, like that. And what you're doing is you're saying the transpose is the transpose in the computational basis. And that's not the same as the transpose in another basis anymore. It is true in the qubit case that the transpose in the Z basis and the transpose in the X basis are the same. It's a coincidence. Well, it's not. It's a thing about the group, which we'll see in 2 minutes. But we picked that particular choice of transpose. That choice of transpose is the same as saying that we want our cups and caps to be the ones for the Z basis, because the cups and caps give you transposes. And now I will have to point out that they take the form sum from J equals 0 to D minus 1 of Jj. They're written like that. And it's different from the sum J equals 0, D minus 1 of Kj in general, which is the cup for the other basis. And so this is, I shouldn't say different, is it not equal in general? In fact, it's different for the different, actually, let's do it properly. Different for n greater than 2. For n equal 2, it's the same. For n equal 1, it's obviously the same because it's all trivial. It's just the complex numbers. And for n equal or greater to 3, then it's D. Oh gosh. Oh gosh. Thank you. D. Thank you. Wow. This is sum j equals 0, d minus 1 of the bra jj, just to be clear. Okay, so transposes are no longer the same, which means that in order to transpose the legs of an X spider, we will need to change it in some way. So what is a piece that we'll use to change it? Well, we've not yet defined everything. So for example, we're not asked what happens to the Hadamard. Originally, if we did the Hadamard twice, we got the identity. And now we can ask what happens in the general case if we do HH. What is this map? Well, we can write it. It's sum j prime equals 0, d minus 1, sum j equals 0, d minus 1. And then we start with j, turn it into chi j, inner product with j prime, turn it into j prime. So this is, okay, this is kind of interesting. It's nice. Chi. Thank you. Is interesting. Okay, the intermediate thing we can already compute. It's e to d minus I j prime times, sorry, 2 pi. Let me just write it as it's chi j prime dagger or conjugate, which is chi j of j prime conjugate, which is chi j of minus j prime. There you go. So that's that particular scalar, and that's where we get our sum over j, really. So our j's, we use the fact that the sum of the roots of unity give you the delta functions. So we use the fact that if we sum chi j prime or minus j prime in this case over j prime, for example, we get 0 or 1, depending on whether j is equal to, j is different from 0 or j is equal to 0. Okay. So this gives us the sum over j equals 0, d minus 1 of minus j. And now this is a map that we will define to be the antipode. The antipode is the group inverse. This is the antipode, which is equal to the group. It's effectively the group inverse. So it sends j to minus j. Modulo n, of course. These are all modular operations, just to be clear. So we learned that the Hadamard twice is the antipode. So we define the antipode to be twice the Hadamard. And we can ask, what is the antipode twice? Well, it's fairly easy to see that it sends j to minus j to minus j, which is equal to j. So it's the identity. And so we learned that actually, if we do the Hadamard 4 times, so the Hadamard dagger is equal to the antipode followed the Hadamard, or the Hadamard followed the antipode. So it's the Hadamard 3 times. And the Hadamard 4 times is now the identity. So this is the slightly more general case. And this is a fact that holds for all dimensions. It's actually quite interesting that there is no weird relationship between the Hadamard and the dimension of the group. This is true for every abelian group, every finite abelian group. And in fact, quite a lot of compact and locally compact Lie, abelian Lie groups have the same property. You do the Hadamard 4 times, you get the identity. The Hadamard twice is the antipode. So that's the thing. But why is it that in the case of qubits, we got that Hadamard times Hadamard is the identity? It's because the inverse modulo 2 is the identity, right? any element, twice an element is itself. So in the case of D equal 2, you get that the antipode is the map that sends J to minus J, but that is J, because -1 is equal to +1 mod 2. And so the Hadamard twice is just identity. So that's a special thing for the qubit case, not for the qubit case.
What is the depth of this statement physically?
In what sense? Of
That
the
if you do the Fourier transformation before is equal to 1.
yes, and if you do twice, you get the same but with the group inverse.
Yeah, but we know there are some models. You take, physical models out of this degrees of freedom.
Yeah.
We know that something called the clock model.
Yeah.
Recognize that 1, 2, 3 is fine, but 5 is a special form. Okay, for example, there is a change in the nature of the phase transition in those models.
Okay.
We go from a standard phase transition to cosine phase transition, for example.
Okay.
So there must be some depth behind this property that has physical consequences.
To the fact that the fourth power of the Hadamard is the identity. In fact, to the fact that if you do the Fourier transform twice, you get a transformation that flips both position and momentum,
Exactly.
which is it's the spatial, it's the mirror symmetry.
It has consequence. If you
Yes.
have degrees of freedom like this, it has physical consequences, and you understand the depth of that statement.
Yeah, I have no idea. But it's interesting that, of course, because you'd get that is a special case, like the fourth.
All these guys do also, with conformativity.
Indeed.
Okay, and I don't understand this.
Yes, but I don't know. There is definitely something, but I've never really.
Curiosity then.
No, I observed that it's a special case that must have some implication. It can't be a coincidence there. It's as if, in a sense, the Hadamard acts as I, right? There is a sense in which the Hadamard is. To be fair, it's not even a statement that you can't. It's a statement you can make precise. There is a group homomorphism that takes the cyclic group of 1i minus 1 minus I, so the phase group, and embeds it into any dimension by mapping I to the Hadamard. So it is very much the case that changing from position to momentum is multiplication by I, and this has all sorts of implications for integrals, for example, where you can swap the two views by adding a phase, like a pi over 2 phase. But there's something more there. Yeah. Anyway, this is where the group inverse comes from. So you get that the antipode is the group inverse, and it's interesting to figure out what another way to write the group inverse is. So I want to send first. Let me tell you what this cap is now. What is this cap? This cap takes J and K, and sort of what happens? Well, we can expand it a little. We can use fusion to unfuse. Okay, we unfuse a delete map from this, or a counit from this. And we write it like this. And this is maybe a bit easier to understand, because at least it tells us that we take J, K, then something happens that adds them. It becomes J plus K. And then the question is only what happens with the counit. What is the counit? Well, the counit is the adjoint of the unit, da. So it's the adjoint of the zero state. So it's the zero effect. So what we're doing is we're testing against zero. So the effect of this map is that it sends JK to either 0 if J is different from minus, actually, let's say to 1 if J plus K is equal to 0. So 1 if j is equal to minus k and 0 otherwise. And these are both complex numbers, okay? So it gets me a scalar. It's the delta that selects an element and its inverse. So if I can find a way to, and obviously the cup is the sum over j of j minus j. I mean, it's just the adjunct. Now, is there a way that I can use this fact to construct the antipode? Clearly, there is a way to go from j to minus j using the cap or the cup. So as long as I put them together the right way, I can probably construct the antipode. And I'm going to wait before I move to the next slide. In fact, I'm going to continue here, I guess. So if I want to have a map that takes j and somehow maps it to minus j, what I can do is I can put a cup somewhere, for example, like this, and then hope that what I feed into this is j, and what I get on the other side. So if j comes in from here, it becomes minus j on this side and comes out as minus j. So all I have to do is figure out a way of plugging a computational basis state without changing it. Well, that's what the cap is for. The cap is just makes the computational basis states flow around. It's the transpose for them, so they're invariant under it. So all I have to do is really use the band of wire like this, but I will write it explicitly as that. So it turns out that the antipode can be written that way. So it's the cup of one color and the cap of the other color. And like, tell me when you're. Is this water that I can drink? I'm going to rewrite it on the other page anyway. So again, the antipode can be written in 4 ways, it turns out. You can check that these are all equivalent. You can write any combination of a cup and a cap. And as long as the 2 structures are commutative, or at least one of them is commutative, and which is the case for group is nice, then they are all the same. So these are 4 ways of writing the antipode, which helps us to understand how you do transposes of the X spiders. So the X spiders, say that I now want to take an X spider with a bunch of legs, and I want to transpose one of its legs down. What happens? So take this spider, the dot, and I want to write this. What is that? Well, first I expand the leg into its real definition. Now this is the Z basis leg that I use to transpose. So that's kind of important. And this doesn't yet help me. But what will help me is if I can somehow introduce some X spiders there that I can then fuse in. So what I can do is this is just the definition of the cap, which is defined to be the cap for the Z spider. And now I can introduce a snake. Introducing snakes is great. It always helps. I want to introduce a X spider cup and an X spider cap, and I will use the cap to do my transpose and see what's left. And so I will take the spider and I introduce a cap in the X basis, then a cup in the X basis, then I have my original cap in the Z basis. And now I can fuse along this leg, and I obtain a spider, which is now a spider, an X spider with a transpose leg and something. So a transpose leg that has this weird snake with alternating cup and cap. And I know that this weird snake from the line above is just the antipode. So what I learn from this is that transposing the legs of an X spider introduces a group negation in the legs. That's the price that you pay for working in dimension different from 2. It's not a high price, but it's enough that people try to find ways to avoid it. You definitely have to be careful the direction of the X legs. They are not. You can no longer bend legs up and down as you wish. You can do it for the Z spider, but not for the X spider. And in particular, the C naught is no longer self-inverse. it can't. But it will, trying to invert it will teach us something. So if I now write the C naught, I will write it as, it's not entirely clear what a C naught would be in this case, but I'm going to define it to be the map that takes J and K, computational basis states, copies J acts as the control, and then adds J and K together into J plus K. In the qubit case, the J plus is J XOR, so this acts as a NOT. This becomes a control add, if you will, or just an add. And then I have a different map, which is obtained by taking the adjoint. Now, this is probably going to be unitary, so it's a good guess. Well, we don't really know that it's unitary, but we will soon learn that it's unitary. So it's a good guess that its inverse is probably that. It's probably the version that you flip the adjoint.
Let me ask you, so the fact that before we could go around,
yeah,
related to the fact that any of the other operator square is equal to 1. Like 1 now is no longer true.
No, correct.
It's operated to the d minus 1.
Yeah.
Therefore, it's important to keep track of the direction.
Only of the X spiders.
Only for the X.
For the Z spiders, you don't care. Sorry, I should have.
Okay, so why?
Because I picked the transpose. When I made the choice of a transpose, I had to pick a basis in which to do my transpose. And I said, I'm going to do it in the Z basis. So in the Z basis, if I transpose the spider, what I introduce is a Z cap. And the Z cap fuses. And I get that spiders in the Z basis now transpose nicely, while spiders in the X basis don't. So it's the fact that I had to make a choice for what the cap and the cup are. So which in terms of matrices is a choice for the basis in which I take the transpose, which is not a basis invariant operation.
Yeah.
Unlike the adjoint, right? The adjoint is the same in any basis, but the transpose isn't, like the complex conjugate isn't. Yeah. And so now I had to pick a basis. And the basis is the fact that my cap and my cup are defined to be the ones for the Z spiders. So for the Z spiders, the transpose now is fine. So I don't care what direction the legs go. But for the X spider, I have to care. So one of the two I have to keep. I could have picked the third basis, in which case both spiders would have to keep the direction. That would have been, I mean, maybe sometimes that's useful physically, because sometimes you have like, I don't know, time inversion means is in the basis different from position or momentum. So you want to have a different kind of transpose. But here it's just a choice that we make, and I made this. I could have made the other one, in which case the Z spiders don't have their legs bent, the X spiders do, but they're dual to each other. So here I don't think we care.
So, but there is a connection to time reversal invariance.
Yes.
Time reversal, the time reversal operation of quantum mechanics.
Indeed.
So
it's a transpose in a very specific basis.
Yeah.
But it's neither the position basis nor the momentum basis. It's a different basis because you have more degrees of freedom because you have CPT, right? You have a charge degree of freedom, you have the parity degree of freedom for the spin. So you have to pick the correct basis in which to do the transpose for the time reversal. And it happens to neither be the position basis nor to be the momentum basis. So in that case, your transpose is going to change the leg, introduce a factor onto the legs of both the position spiders and the momentum spiders. Because you're using a basis that is different from, correct, exactly. And that, by the way, that factor is just going to be the factor that converts CPT symmetry into the action on the position and on the momentum basis. That's what the factor is. So here, the inverse, I could show to you that the inverse does the correct operation, or I can diagrammatically derive that the inverse does the correct operation. So let's do that instead, shall we? So what I first do is I bend my wires so that I have something like this. That's fine because I can transpose the Z spider, but I can't transpose the X spider without introducing an antipode. So what I get is an antipode and then an X spider here. And it kind of makes sense that it would work because I take J, copy it through, becomes J here, becomes minus J here. I have K, copy through, and add it to minus J. And what I get is K minus J, which is the inverse of K plus J. So that's fine. That is at least a sanity check, but I want to prove that this works. So I want to see which rule I have to add in order to prove that this is correct. So let's see. I compose both of them together. I fuse, and I get something like this. So it's different from the qubit case, because now I have the same as a leg chopping operation, the same as a bialgebra law, sorry, as a Hopf law, but there is an antipode on one of the legs. And so I would like to be able to say that this results in chopping the two legs, and I get the identity. I would like to do that. So what's the rule that I have to introduce? Well, the rule that I have to introduce is the Hopf law for a general group. And the Hopf law for a general group says that if I have a Z copy and I have one leg that goes to an X multiplication, so multiplication of the group, and the other leg goes through the inverse, what I get is just a disconnection. And this makes total sense, because if I look at the computational basis, I have J, I copy through onto J here and J here. The left of the group addition has a J, the right of the group addition has a minus J, and what I get out is J minus J, which is always 0, independently of what J is. So it's the same as saying that like J in, I map it to the scalar 1, and then I map the scalar 1 to the state 0. So these are all cats, obviously. Typically I don't care, but here it becomes confusing. So this is the new Hopf law. And in general, you get the Hopf law in here. I don't have to care because this is an abelian group, but you can generalize this, and then you have to put a twist in between. But so for Hopf algebras, you can generalize this to something that works for arbitrary Hopf algebras, but there's a braiding in between. It doesn't matter here. We don't have to worry about it. And of course, because they are commutative, we also get the antipode on the left, and it also works. But these are commutative structures, so we don't care. Fantastic. So this is the general Hopf law, and now we can also prove that actually what does it mean to invert something in modulo n? So sorry, modulo d minus j is, I can write that it's d minus j, but that's kind of boring. Can I write it in such a way that it's a product of factors? Yes, I can. I can say that it's d minus 1 times j, right? Mod d, that's true. So it's also true that if I write my antipode, that's the same as taking one computational basis state and making d minus 1 copies of it, and then adding them up, because this takes j, copies the state into d minus 1 copies, and then adds them up into d minus 1 times j. So, and I learned that actually there yet another way to write the antipode is just take one state, copy it many, many times, add all of them up, and that gives me the inverse again. So it's one of the axioms that you derive for higher dimensional, that you have to introduce for higher dimensional calculi, is this observation that the inverse is d minus 1. Okay, so this is one. We also have the bialgebra law. The bialgebra law is exactly the same. It's just the observation that if I take j and k and I make copies, I get j, k, sorry, j, oops, j, k, k, j, k, j, k, j plus k, j plus k. So either I first make copies and then I add, or given that the addition results will all be the same, they all have the same factors, sorry, the same added summands, I can first do the addition and then copy the result, and that is exactly the same. So j plus k, j plus k, j plus k, j plus k. And now I can generalize this, and that's okay. In a sense, this is boring because it's the same rule that we got before, but I can take the opportunity to give you the general version of this rule. And the general version says that if I have any number of copies on the left and any number of copies on the right, and I connect them with a KNM bipartite graph. So each one is connected to each copy on the left is connected to each copy on the right as KNM. Then this is the same as having a single addition with n inputs and a single copy with m outputs. And again, this is the same because you can take J1 ... Jn, and each of the wires that come into an addition will have J1 ... Jn, and the result will be J1 plus ... plus Jn. So this is why it's the same. Why is this a good way to write it? Well, because it gives you for free a few interesting cases. It gives you for free the case where there's zeros, for example. So I take that. I wonder if I can copy from one slide to the other. I believe I can. Let's do this. Fantastic. So I remove my indices, no longer necessary. And instead, I make an observation, which is that I can take this special cases of this rule, which is now a parametric rule for all n and all m. And I can say what happens when m is equal to 0. When m is equal to 0, I get the following. When n is equal to 0, I get the following. So on the left, I have and when n and m, sorry, n is equal to 0, m is greater than 0, I guess I should have said. When they're both 0, I get the following. Nothing on the left, so the scalar 1 in the complex numbers. And well, some, to be fair, I'm omitting some scalar, which is non-zero, and I get the bone on the right. And if I pick my normalization factors the right way, this becomes the scalar root n. Sorry, 1 over root n. Root n? 1 over root n? Root d, thank you. This is actually the scalar root d in the complex numbers. Because it is the inner product of chi 0, 0, which is 1 over root t. Sorry, it is 1 over root t. I work with a different normalization convention. So good. So those are consequences. What are these copy laws now? What do they mean? Why are they? What is their significance? Because the beauty of it is that they have some group theoretic significance. We have a copy law that says that if I take any of these computational basis states, so I'm going to write the phase for an element J. This is Fourier basis, but yeah, sorry, I shall start again. I'm going to define there's a spider, these spiders. Let me do it properly. You're right. You're completely right. The first time that one sees this, it's just confusing. So let me do it slowly. So there's alpha. Okay. What is this? This is 0 plus e to the I alpha 1 plus e. Sorry, this is chi 0 plus e to the I alpha 1 chi 1 plus e to the I alpha 2 chi 2 plus ... plus e to the I alpha d minus 1 chi d minus 1. Actually, I had it right the first time. Did I have it right the first time? That's the yes, it has to be in the x basis, correct. So chi 0. That's right. So it's that, which looks weird. It looks odd. It's just some weird state, some weird state with weird phases in the 1/√10 in front. In fact, these ones don't have the 1/√10, so it's just a. So up to a normalization factor, it is some state, some superposition of states in the Fourier basis. Now, if you are careful with your phases, then you can obtain computational basis states. So if you set alpha, in fact, you can check the correct states to pick by saying that if you have this and you, let's just do it the right way. So if you set alpha j to be j minus j k over n, sorry, alpha j to be minus j k over n for all j, that gives you what? It gives you that this state is chi0 plus e to the I minus e to the minus I 2 pi, I guess 2 pi j k over k over n chi1 plus e to the minus I 2 pi 2k over n chi2 ... which happens to be just the computational basis state k. Because it's the same as doing you do the Fourier transform, you go from computational basis to Fourier basis. You do the Fourier transform with the negative index, you go from the Fourier basis to the computational basis. So it's the inverse Fourier transform. And so actually some of these states, some of these states are just weird phases, but if you pick the phases really well, then you get the computational basis states again, which is kind of nice. And we already have a definition for this alpha phases. And I'm going to write as I take chi minus j as the phase, which is kind of right. I'm just going to write it as j. And this is the state j, where I define this phase to be 2 pi minus jk over n by definition. So it's a way of saying I identify the computational basis states with some of these spiders, exactly like the 0 and pi spiders for C2. So for d equal 2, you have that the 0x spider state is the 0 computational basis state, and the pi x spider state is the 1 computational basis state. In general, this is true, but you get more than one angle, and they have to be selected in such a way that they give you the inverse Fourier transform. And similarly for the x basis states, you have the direct transform. So you have this one is defined to be, well, it's not defined to be, it's equal to j, and I'm going to have something similar for the Fourier basis ones, where again I define j of k to be 2 pi minus jk over n, and I define k of j to be 2 pi kj over n. And that's it. Huh?
It's over the,
thank you. No, do say that. I'm sorry, I'm so over D. Did I say it here too? It's just habit. It's bad habit, but and yeah, I even use the thank you that. And so now I can ask, what does the copy spider do? Well, the copy spider in the Z basis copies all of these phases. So it copies the computational basis states. That's obvious because it's the spider in the computational basis. So it has to copy the computational basis states. And the lead spider in the Z basis deletes the computational basis states. So it's the empty diagram, but I'm going to write it as the scalar 1. Be clear? And now the question is, what are the other rules? I could just say, yeah, okay, the other rules are simply the fact that the spiders in the X basis are I will copy and delete the states of the Fourier basis or the X basis, that is not particularly satisfying. Because that's like, sure, it is true, but I'm going to say, okay, what does it mean that I have this rule? I'm going to do them in reverse. And I'm going to say, what does it mean that I have this rule? Question mark. And what does it mean that I have this rule? What do these rules mean? Well, instead of thinking of them as copies, I'm going to say these are rules from group theory. This rule here is the same as saying that if I have a character and I plug J plus K in it, it's the same as plugging J into it and K into it and then taking the product. So it's the statement that chi K of J, I plus J, A plus B. Let's do A plus B. A plus B. It's the same as saying that chi K of A plus B is chi K of A times chi K of B. And similarly, the rule that says that if I apply to the unit, I get the scalar 1 is the statement that chi K of 0 is equal to 1. And then there's a third statement that you can derive, which says that if I take, if I want to take the character and I transpose it with the Z basis transpose, I get the adjoint of the character. And that's the same as saying that chi K of minus J is chi K of J dagger. Because that's not the, that's not the, that's actually this one. It's chi of minus K J. Because the adjoint negates the K, that it changes the phase. It's just it's a conjugate in that basis. And so I get that particular statement. So they are the three rules. So copy, delete, and transpose for these states are exactly the rules for multiplicative characters, which are group homomorphism from ZD into S1. So that's the statement that they are, that they respect addition, they turn addition into multiplication, send 0 to 1, and they turn conjugates into inverses. So that's those are the three statements that you get. So these are the copy rules for the ZX calculus, and there's nothing else really. I mean, these are all the basic rules that you need. There's they all effectively come from group or representation theory. And then you can ask, what is the Pauli group in the qubit case? So what are all the possible combinations for the Z rotations and the X rotations, right? So what are the possible combinations of these? Well, certainly all the possible combinations of these ones form a group isomorphic to ZD. All the possible combinations for these ones also form a group isomorphic to ZD, because you do the rotation D times, you get D times J, which is 0. So that's the same group. Then you can ask, what about compositions of these rotations, which are the equivalent, if you will, these are the equivalents of the Z basis. These are the equivalents of the Pauli Z's. These are the equivalents of the Pauli X's. And these would be the equivalents of the Pauli Y's. Up to a phase, in fact, there is because Y is not defined to be Z times X, right? Y is defined to be Z times X times minus I. There's a choice of a phase that kind of normalizes things. And so you can ask diagrammatically, can I just quickly derive the compositional structure of these transformations? And indeed, you can prove that you can use by algebra, as usual, to prove what it means to compose two of these. So let's say A, B, C, D. And what you want to do is you want to effectively invert these two. You want to swap them, to commute them past each other, braid them, because there's going to be a phase that comes into play, but you want some kind of commutator, and this commutator is going to allow you to rewrite it as some phase times A plus C, B plus D. Now that commutator, so this is a phase that we have to figure out. How do you figure out that phase? I already kind of mentioned it yesterday, but today I can properly prove it. I'm going to take the two phases and take them out. Like this. And I can use by algebra to replace the center with the square or the bialgebra. Then I can use the copy laws to copy through the two, the state and the effect. I will. Thank you. Yeah, that's a good suggestion. So here I'm using the fact that and can I let them have the slides afterwards? Because I have collected all of them. Would you want to put them on the website? Yeah. So I'll send them to you, because then these can act as a reference for future use, more than just of course you can watch the video, but if you just have to quickly sort of go to it's easier to. And so then I copy through, and here there are two rules that I apply. One of them says that I can copy the computational basis states. I intentionally picked this direction because it's the one that makes sense in terms of characters. And I can co-copy or co-multiply the character. So I can use the multiplicativity property for the character to remove the part of this weird braid and simply get C guess plus fusion, C, B, so I commute them through, but I get something out of it, which is this scalar here, which is it's just a phase, and I can compute exactly which phase it is. So I get the scalar, and my scalar is just this bone. And if you check the various definitions, this is going to be proportional to, of course. With the correct factors, I can just ignore the proportionality. It's e to the I 2 pi b c over d. So that's the braiding from the, sorry? I was tempted to make that exact joke, but then I thought I already made this mistake too many times. They will think that I am really saying n. And in general, this is the discrete version for the clock matrices of the Weil canonical commutation relations. So it's the same braiding as the Weil CCRs. So I'm gonna say that it's the Weil CCRs for this particular setup. So I have this braiding, and you get that scalar, and you can correct it if you want, and you can get Y matrices that compose the right way. How do you do it? Well, you say I start with I take Y A B and I define it to be this matrix, and then I ask what Y A B to the D is, and I get this matrix. So I get this very long chain of things, and I'm going to, I guess, conclude with this because it's kind of we can then get to questions, and if you're interested, I can And so I ask, okay, how do I get this into something, some scalar, which I'll have to cancel out, times the identity, because it has to be the identity. I mean, this is there. If I didn't get, if I don't get the identity, then I've done it wrong. So clearly I have to get the identity. The question is, how many commutations do I get? Because each commutation picks up a factor of e to the I 2 pi a b over d. And I just have to count how many. So this x, so I guess there is an x here that commutes through 1z. Then there's an x before it that commutes through 2z's, dot, dot, dot. This one commutes through d minus 1z's, and this one commutes to d minus 2z's. So the number of factors that I pick is 1 plus 2 plus 3 plus 4 plus d minus 1. So it is d minus 1 times d over 2. So the overall factor is e to the I 2 pi a b over d times to the d minus 1 times d over 2. And so what I want to do is I want to spread that factor across. I can just rewrite it as e to the I 2 pi a b d minus 1 over 2. And I want this to be 1. I mean, I want to spread it. I don't want it to be 1. I want to spread it so that I add a factor of alpha here. So I have a factor of alpha d here. So I have a factor of alpha d here. And I want alpha to the d times this to be times that factor. I want this entire thing to be 1. So I want the whole calculation to just give you the identity without a phase, because that's what happens in the qubit case when you define y to be minus I times zx. So all I have to do is pick alpha equal to e to the minus I 2 pi ab d minus 1 over 2d, sorry, over 2. And if you do the calculation for the qubit case where a equal 1, b equal 1, d equal 2, that gives you alpha equal plus or minus I, depending on your choice. So it doesn't really matter because the minus, when you square it, goes away. So that's one of the possible choices. So you can define all the Pauli matrices in the qubit case. And the beauty of this is that if the beauty of it is that if d is odd, that is the case of any prime other than 2, then 1 over 2 is actually an element of d, of mod d, of z mod d. So you can invert 2 because it's 2 mod d has an inverse. And so this is actually an invertible element mod d. And so you can actually write an element. This is going to be some, because effectively d minus 1 is divisible by 2. So this is a number. This is just a number, and this is just a scalar that you can write down. So you can define the x, y, and z matrices. So the Pauli group, if you will, for arbitrary dimensions by just using the ZX calculus exactly as you would in dimension 2, but taking care of using bialgebra effectively to derive the correct braiding relation for the matrices. So these become your ZAs, your XBs, and this becomes with the correct phase, which is, if you give me a second, it's going to be A, B, D minus 1 over 2 times 1. That. And this is YAB. And this gives you the Pauli group. So this is the Pauli group in the algebra over ZD. And I'm going to stop there. This is going to be is effectively the generalized QD ZX calculus. Now, if you want to make it complete, you have to add a couple more rules to define a triangle or the W spider. But for like to do interesting group theoretic or representation theoretic stuff, this is a good start. Okay, if you have questions, we can online as well. I'm happy to answer them, or otherwise I can say some more things on these lines, as you wish. I believe they're still generated by all of the control adds plus all of the single qubit rotations in the Pauli basis divided by 2. So you take the square roots of the Paulis. But there are some people who know this better. I mean, I can tell you what it is in abstract. Giving you the generators is not really my. There's a recent work on it that I can pull up and give you as a reference. There's a nice work on stabilizer. So Clifford and stabilizer QDIT ZX calculus by Cole Comfort. So I can make it available. I'll write the citation. Yeah, because it's in fact I think it is. Was it? Let me check. So it is going to be Cole Comfort. Yeah. Let's see. Let's hope it's one of these. Maybe it isn't. I don't know. Not a start. No.
You're saying that there is.
Yeah, there is one. There is one. It's definitely on the archive actually. So why am I don't know why I didn't just go to the archive. No. Comfort. Wrong. It exists and you will find it, but you don't have to, because I can just copy paste the. There we go. So this is I'm just going to open it, but I'll just copy paste it into a slide. And it's there for your reference. So ZX for QDIT stabilizers, which has a lot of good sort of symplectic vector theory Pauli's. It's pretty nice stuff. Again, so what else? What about symmetries? Yes, maybe that's something that might be of interest. Okay.
Is there some simple example where we can use this diagrammatic reasoning to analyze measurement based instead of circuit based, measurement based?
Yes.
Simple example.
Yes. Okay. Fantastic. Yes, that is one of the good examples. So let me introduce all of you to the cluster states and MBQC. So let's do that. Yeah, and we can do it for qubits if you'd like.
No,
just qubits. Well, you now know everything. We can do it for qubits very easily. All right. So let's start with one-dimensional cluster states. So you start with the plus state on a few qubits. And we want to find a way to construct a state on these 5 qubits, but in fact, it can be on any number of qubits that has some useful form of entanglement that we can exploit to perform computations just by doing measurements. We want to create a cluster state or a graph state, but cluster states are the canonical example. So one way to do it is to say, okay, I'm going to apply some control Z gates, which we've seen this morning, and I'm going to apply them in pairs, first between the even odd qubits, then between the odd even qubits. So like Q0, Q1, Q2, Q3, Q4, Q5, that's the first layer. And then the second layer is going to be Q1, Q2, Q3, Q4. And that's it. And now this I claim that this is a useful entangled state, that is a nice entangled state, and you can immediately see, if you remember some of this morning's tricks, you can already see what this simplifies to. It's a chain, right? All of those spiders fuse, and I am left with a chain of spiders connected by Hadamard gates. And then there's legs coming out. So these are my qubits. They form this weird chain state, which is it's called the one-dimensional cluster state. And then we'll generalize it to 2 dimensions and 3 dimensions. It's a special example of a graph state, which is a state done with X and Z spiders. And so you can slightly generalize it, but we don't need to do it now. Now, what can I do with this cluster state? Well, I observed that there is a funky thing I can do with measurements. So I can take 2 qubits, connected by a Hadamard, and say that this qubit starts in the plus state, and this qubit starts in some state. So there's a qubit coming, there's a qubit flowing in, the qubit state flows in. I don't know what it is, but what I can try to do is I want to kind of make it go onto the other qubit. I want to kind of make it go like this, maybe up to some correction that I have to make. And what I can do is I can measure this in the X basis. And if I measure it in the X basis, what I get is either 0 or 1. And depending on whether I get 0 or 1, the result is some kind of teleportation. It's going to be something like this, and then Hadamard, like that. So up to some correction, this performs some kind of teleportation. And that's, yeah, it sounds like in teleportation, you would go, okay, correction here. And the correction would look like perhaps Hadamard followed by B pi. That's what the teleportation protocol would do. However, we might just say, hang on, I don't want to correct anything. I want to try and use these to do some computations instead. So I want to think, what happens if I start from a qubit, a few qubits that are entangled in this weird cluster state way, and I start measuring the qubits. And I measure them, and let's say I measure the first one in the X basis and obtain some B pi. Then this is equivalent to, you fuse the B pi state, and then you have a Hadamard, and then you have something in the remaining of the chain, and that's okay, but that's not very interesting. What if instead I do a measurement, but I do it with some angle? So I get alpha plus B pi. I still have some randomness there, but now I have some control. Instead of measuring in the X basis, I first do a Z rotation by alpha, and then I measure in the X basis. So I do something like this. I first rotate, and then I measure in the X basis. Then what I get is something slightly different. I have control over the phase of the state. I don't have control over this pi, but this pi is an error, really. Okay, there's nothing too bad about it. What I can do with that pi is I can push it through the Hadamard. So I can take that phase that I don't want, and I can push it through my Hadamard. I can keep my alpha Hadamard here. I can push my B pi and change it. And then I can push it through. First, I push this through the Hadamard, then I copy and push it through, and I push it forward and forward and forward. And what I do is I say, okay, I just have to remember that the next thing I do on the second qubit, I'll have to take into account the fact that there was some randomness. But I already did the first measurement, so I already know what the bit is. I will do my measurements one after the other. And so I know what B is. And when I do the next measurement, I can sort of correct it, but I only correct it in the measurement. And then I sort of push it further and further and further. And so I just push it here, cross the Hadamard, and it sort of fuses with the next one. And here I will not, maybe I have to care about it, maybe I don't have to. And then this first part becomes this state. And now I have a second stage of the measurement. And the idea is that I will continue doing measurements. And the effect of these measurements is up to some errors, some Pauli errors, either zeros or pi's, that I can correct later. I will be able to apply rotations to my qubits. But this is not very interesting because it's, yeah, I can continue doing this and I can apply a rotation by alpha and a rotation by beta, and that's it. On 2 rotations, I get an arbitrary qubit state. That's super boring. Now, instead, you say, no, okay, I want to do arbitrary computation with this method. And in order to do arbitrary computation, I have to be able to do single qubit gates and 2 qubit gates. So I need to be able to have a state, a cluster state, that I can consume in 2 ways. I have a direction, which is the direction of the qubits, the wires in my circuit, and a direction, which is the direction of time in my circuit. But it's not time, really. It's just the direction that I make out to be time. So I prepare my qubits in a state that is, again, a cluster state, but now it's a 2D cluster state. So I start with, I will effectively indicate that there's a grid of qubits, and I'm going to take a square grid because square grids are the best. They're just easy. They just work very well. And this square grid is going to have qubits on its vertices, and I'm going to indicate the fact that there's a qubit by having legs that sort of jet out diagonally. So imagine that this is seen in some isometric perspective from the top. And the entanglement of the qubits now has 2 directions that I can write down. It's a bit boring to write all of it, but for the sake of clarity, I'm going to explicitly write all the Hadamards, so you remember that those are Hadamards. But once you start working enough with these cluster states, people adopt a notation by which they have a solid edge for a normal edge, and they have a dashed blue edge for a Hadamard edge. So you start getting, if you go into some more advanced ZX calculus papers, you're going to see edges written like this, and they are defined to be Hadamard edges. So it's as if there's an H, but at least you don't get all of these H boxes that fly around and clutter your notation. But for now, given that we are learning, I'm going to. So let's say that we have 4 layers, because I think I'll need 4 to do what I want to do. And now the trick is going to be that we'll want to perform measurements only on these qubits, only measure them in such a way that a computation appears. So we want to end up having, say, some entangled state or a Bell state. Let's try to make a Bell state. I think a Bell state can be done with just these many, right? Yeah. Fuse, yeah. I want to get this to be effectively a Bell state on some of the qubits. So I want to, just by performing measurements in appropriately chosen bases, I want to consume this carve, as they say, this cluster state, so that I end up only having a few qubits in the Bell state. And my computation proceeds by carving. I will remove some sites that I don't need to create gaps so that the qubits are separated. And I will fuse some spiders in such a way that I create CNOTs or CZ gates or Hadamard gates. So the idea is I want to measure these qubits in such a way that I get that the right gates appear out of my circuit as I carve through it. So what are the tricks that I can use? So I make 2 observations. The first one is that if I have one of these, I focus on one node only, okay? That's the trick. You start, instead of looking at the giant complexity of the grid, you look locally, and you hope that these operations can be performed locally. And I ask, what happens if I perform a measurement in the X basis? So what I'll get is in fact, in the X basis. Okay, yeah, let's start with the X basis. I'm gonna make a few copies of this so that I can easily write all of the things I want. So copy, paste. Copy, paste. I think that is enough. So if I just measure it in fact, let's start with 2. Why complicate our things? I just measure it in the X basis. I'm going to get a phase that I will be able to safely ignore for reasons that shall be discussed shortly. That's the point of it's called just the correction phase. And what I get up to the phase is that the qubit effectively disappears, but the site in the grid remains there. So up to an error, that's a multiple of pi. It's important that it's a multiple of pi because multiples of pi are copied through spiders and they just go through the Hadamard. So I'll show you how to propagate them so that you can then correct them in further measurements. But for now, just say you can disregard it for now. Just ignore it for a second. The other thing I can do is I can measure in the Z basis. And again, there is a multiple of pi there. And what happens if I measure in the Z basis is more interesting. It removes a site from the lattice. So you have to imagine that here there are more neighboring sites in the lattice. And what happens is that X spider gets copied. So I get, let me just do a copy paste of the entire thing. It's going to be a big, no, undo, copy. I can do it. I can do it. Copy paste. Excellent. So I'm going to get the same thing, but that particular spider state, computational basis state, gets copied 4 times. Okay. So I now have b pi, b pi, b pi, b pi. And then what happens in each of these? So there are four individual pieces that I have to consider, but they all do exactly the same thing. Each of them starts by having state, Hadamard, next node, then the state changes color, and then it fuses with the next node. So I remove a site as a consequence of my action. But what I introduce is potentially some other nodes, some of the neighboring nodes or that node will have some error on them. So each node will have some error, but I will not care about these errors because I can move them further in the lattice. I can make them a problem for the next measurement, which is going to be the point. So now I have these 2 operations that I can perform. And with these 2 basic operations, which are going to be remove, so keep a node in the lattice and remove a node from the lattice, I am able to do a bunch of stuff. But first, I have to slightly generalize this to an arbitrary rotation followed by a measurement, because I want to be able to introduce some phases in the basis. So this becomes I keep the node, but I introduce a phase plus an error. But the error I don't care about, as I said. And we'll see right now why I don't care about the error. And the other operation that I want to have is this delete operation. So I can remove nodes from this lattice. And the delete operation is what I use to carve the lattice. So this is the measurement outcome, and I introduce some errors onto the neighbors. Okay, so these are the 2 basic operations I have. Why do I care? Well, because going back to my first, I'm going to tell you why the errors don't matter. So I can ignore them. I will do the Craig Gidney thing. It's like guy who works in error correction a lot, and he has a habit of just completely ignoring these Paulis. In fact, he went and developed a variant of the ZX calculus, which is Pauli free, so it doesn't have any of these pi phases. You can't interpret it in linear maps, but you can interpret it in stabilizers, which is what he uses anyway, so it works fine. But you can disregard them because once you have a phase on one of these nodes, which is a an error, I'm going to call it. What you can do is you can push it through the Hadamard to the next node where you're going to do the next measurement. So imagine that there is a measurement coming afterwards. So I'm going to push it to the right because that's the sensible thing to do. And what you get is that the error disappears from your node. The Hadamard remains there. And now you have a different colored pi gate on the other side of the Hadamard. And this different color pi gate gets copied and propagated forward in the computation. So you push some of it fuse it onto the other neighbors, and some of it you push onto the measurement. And so all you have to do really is make sure that next time you measure something, you take that error into account. So here you have the pi that you're going to need to cancel. So instead of performing, when you do the next measurement, before you do the measurement, you're going to, oh, interesting. I'm finishing my juice because I forgot to plug in my laptop. But I'm going to make short work of that. So the next measurement you perform, you're just going to do if there is an error, which you know because of the previous measurement outcome, you're just going to apply an OF gate, and you're going to remove the error from your computation. So that's just for next measurement to take care of. You don't really have to logically imagine that that's there. Come on, and you're done. And so now what you've done is you effectively propagated the error further in time in the computation. So there's going to be a B pi here, B pi here, B pi here, and B pi here. And this is just an error that you don't really care about because you can't remove it. So the idea is there is an error due to the fact that the measurement outcome is uncertain, but that error you can just push further in the computation and remove logically by doing a NOT gate at before the next measurement. So you can completely disregard it. And so we go back to our cluster state. And so we say, okay, this cluster state, I hope I have enough gates in here. I think so. But yeah, well, if we don't have enough gates, we're going to add more. So first things first, I want to create some, let's say that I want to do the following computation. Okay, I'm going to ideally want to perform a computation where I start with 2 qubits in the plus state, and then I apply a Hadamard, sorry, a C0 gate between, sorry, CZ gate between them, and what I get, and then I apply, let's say, a Hadamard on one side, so that what I get is this, which is the Bell state. Okay, so I want to obtain the Bell state, but I want to obtain it by carving the correct number of operations. And so now I have to hope that I've done this right. Give me 1 second to check. That disappears. That gives me the Hadamard. That disappears there, and yeah, I need one more. That's Hadamards, blah, 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 blah. That can, yeah, no, this is fantastic. I think I've done it right. So what I do is I start by measuring this qubit in the C basis, sorry, in the X basis, this qubit in the C basis, this qubit in the Z basis, and this qubit in the X basis. And the effect of doing that is that these 2 qubits remain there the same, they just fuse in. And these Z basis measurements remove the sites from the lattice altogether. And so I'm left with that. So I carved the bit of the lattice that I didn't care about. In fact, I guess I could be, let me do something slightly more interesting here because this is a bit boring. It's not boring at all, but I can make it more interesting. So let me add a phase so that I can show you that too. Let's do that. I did. So there's this. Now I want to create a C0, sorry, a CZ. So I want to leave a bridge between the qubits, but there has to be some space left after the qubits. So first, I'm going to carve some more space out of my lattice. I'm going to carve away these two sides. And I'm going to keep these two sides. And I'm going to keep these two sides. And I'm going to keep these two sides. And the result of doing this is that this remains, this remains, this remains, this remains, this remains, this remains. So I remove the qubits from the state. So I keep the qubits and I remove these two sides from the state. That's the. And now I can use the rules of my calculus to, in fact, I think I got a slightly different state that I wanted, but it doesn't matter. Did I apply a? I did this wrong. Hang on. Nope, I did this wrong. Apologies. I want to cancel. Yeah, sorry. Let me just try again. It's but it's boring. It's boring. It's boring, and it's a trick that is worth mentioning. It's because what I get is I get unfortunately a copy that doesn't give me any entanglement. So I don't get the plus state. I get because I don't do a CZ. I do a CZ, but in the X basis. So it's not the correct one. So I want this. I want one more layer, and I want to remove. I want to keep these again. Sorry, I want to keep 2 and remove 2. So I want to remove these ones in the middle and keep these ones, because then the two Hadamards will cancel out and leave my plus state at the start, which is what I want. There you go. So you start with this one, and then you say, I push the Hadamard through. This becomes just the identity. And then I can remove the Hadamards altogether because they cancel out, and I'm left with my plus state, which is what I wanted. So sometimes you have to delete 2 layers in order to have Hadamards that cancel out nicely. And now I am in the position to do what I wanted to do originally. So I now delete. I carve away these 2 sides. I keep these 6 sides. And the result of doing that is that I have kept some qubits in the tensor network, and I have removed some stuff in between. So I create some space, and that space gives me my CZ gate. Because see, I now have 3 Hadamards. So first I remove the 2 spiders in between. They're just identities. And then I observe that I have a triple Hadamard. So 2 Hadamards cancel in a pair, and I'm left with a single Hadamard in the middle, which gives me my CZ gate. So that's the carving that I have so far. I also observe that I get a cancellation of Hadamards on the right. So these also cancel out. And then I can also remove the 2 Hadamards there. So I'm left with at least not exactly the state I wanted, but almost. That's good enough for now. So this is almost the Bell state. And then I can continue this game. I can say, okay, now I need to do some more operations. So I look at the next part. These cluster states are typically very big. So I can continue consuming and correcting. Remember that I omitted all of the corrections because the corrections are just done by pushing the error into the next measurements and taking care of the error when the next measurement comes. So now if I want to keep a Hadamard, because I want to actually get a Bell state, I can perform, I want to remove these sides in the middle. I want to carve them out. I want to keep this side here. I want to keep the side after the Hadamard, but actually I want to introduce a rotation as well. And I want to carve out these 2 sides. And I want to keep these 2 sides. There's a Hadamard here. And then there's more Hadamards. And so the result of doing this carving and that rotation, which I think is this is the very cool stuff that happens. If you pick a rotated basis, you are applying a rotation to your qubit. So you have some control that's useful for universality. So you remove all of these. And you remove these, this, and this, you fuse the alpha in, you're left with a Hadamard there, but you can then remove it later on. So you're left with an alpha here. Yeah, there's an additional Hadamard somewhere, it's fine. So yeah, well, almost what I wanted. There's a Hadamard on the top. And so this entire computation gave me, if I now take this state and I sort of collapse it, what I get is, and I show what happens to the rest of the circuit as well. So I'm left with a state that is the state I wanted with a Hadamard in addition that I didn't want, but I can remove later. Hadamard here, and then an alpha here. And then the cluster state continues to exist. So I have still more qubits next after it. So I have qubit here. And how many did I have in the middle? 2 qubit. You know what? I'm going to use blue. It's one of those occasions where it's useful to 1, 2, 3, like that, and they still have their thing. Then there's more, and that's it. And you continue to do this again and again and again, and your computation effectively proceeds by consuming this cluster state. In one direction, you have qubits, so the tensor product. In the other direction, you have time, but the time of the computation. But in terms of the operations that you're doing, all you're doing is measuring the sites of this lattice in either the z basis, the x basis, or a rotated x basis, so an equatorial basis. So you do alpha first and then measure. And you proceed by carving this cluster state further and further, and you compute. So this is called MBQC. So this is cluster state measurement-based quantum computing. And then the reality is that this particular cluster state is not fault tolerant, doesn't allow you to do fault tolerant computation. If you want to do fault tolerant computation, you need a 3-dimensional cluster state instead. So you add one more dimension, and then you use one direction is the two directions are the 2-dimensional lattice of the surface code. Let's say one direction is the fake time of your computation, and you sort of consume your state going upwards. And you pretend that you're doing surface code computing, but you're actually doing it's MBQC, but pretending to do a surface code computation in time. And there's a nice paper by PsyQuantum that shows 4 different versions using the ZX calculus. So I'm going to put a reference to that in the slides. So there's a reference to it's called unifying flavors of, yeah, that was the one. Unifying flavors of fault tolerance with the ZX calculus. I'm going to copy the reference and I'm going to show, no, apparently not. Come on. Copy, and I'm going to show you what this, I hope I'm sharing my screen. I don't know if I'm sharing the slides or my entire screen. So let me share the paper. Yeah, now I should be sharing the paper. So yeah, there you go. And this is from this uses notation that should now be familiar to you. It's just ZX calculus for qubits, but you could do the qubit version, the qubit version. And if you go down, there's a lot of interesting observations as to how measurements, how they use this additional notation to keep track of stabilizers as they propagate across the lattice. If you do fault tolerant stabilizer codes, then this becomes fairly useful. But it's not additional diagrammatic notation. It's just bookkeeping for their own proofs. So these are not diagrammatic elements. They don't compose well. It's just them highlighting where the stabilizers happen. And then you effectively say, I look at my, just for fun, I'm going to show this. You imagine that you have a surface code, a planar, so you have a planar array of qubits, and you're doing the surface code computation on it. The surface code computation on some qubits is applying certain measures. It's performing certain measurements. It's performing correlated measurements on the squares of a lattice. So either z measurements or x measurements, and you apply them in time. And as you apply them in time, these measurements detect errors that you can then correct. And then you say, actually, I don't want time. Time is bad. Time is problematic for many reasons. So what I want to do is, instead, I want to have a giant cluster state. Maybe I produce it with my photonics hardware. I just entangle all of my photons in this three-dimensional cluster, and then I pretend that I am doing cluster state computation. So I pretend that I'm doing surface code computation, but where I take this 3D cluster state, I dedicate 2 dimensions to be the surface code, 1 dimension to be the time, and then I do MBQC exactly as I did today, but you do it to implement the operations of the surface code. And that gives you fault-tolerant MBQC, which is what Psych12 wants to do with their machines. Just kind of, and this is all ZX calculus based. So they recently released this paper using the ZX calculus to show that what they do is equivalent to fault-tolerant MBQC, which is equivalent to a surface code computation. So what they do is the next version. So they take this, they unfuse some nodes, and they show that their mode of computation, which is fusion-based quantum computing, is the same as doing fault-tolerant MBQC on the cubic cluster state, which is in turn the same as doing normal surface code lattice surgery. And that's the way that they effectively explain how their technology will work. They don't have these machines yet, but they plan to have them. Just yes, they are. Yeah, you effectively, it's the same as doing topological. Originally, the fault tolerant. So what is it? The Rausendorf and thank you. The original work did fault tolerant quantum computing by braiding defects in these grounds, in this very entangled ground state. So you took defects, you moved them around and braided them, and the effect was to perform fault tolerant operations. Then a few years ago, they moved to lattice surgery. So they took the surface code, and this is Horstman and a couple of other authors who showed that you can do lattice code surgery, and that is equivalent to doing topological, sort of the fault-tolerant quantum computing by braiding defects. But now you just take patches of the surface code and you merge and split these patches of the surface code, and that it can be used to perform operations. So I think the new trend in surface code work is to use lattice surgery rather than directly use the topological version. That's underneath. It's equivalent. It does the same thing. There is an explanation of the equivalence between the two, but it's slightly easier to work with the lattice surgery. And there's a nice work that I can also reference where lattice surgery is shown to, the operations of lattice surgery are shown to be equivalent to the merge and split of the ZX calculus. So that rough and smooth merges and splits in lattice in surface code lattice surgery are the same as the Z and X merge and the Z and X split of the ZX calculus. So you can reason logically about your logical qubits fusing and splitting by using the ZX calculus, which is what some of the more recent work does. So I think most work by Craig Gidney these days uses ZX code for the high level part of things. So this is they are developing fusion-based hardware. So I think there is a picture of the hardware here. If there isn't, I can go and talk about it on a different paper, but hang on. Let me check first if they show you what this does. Must be, no, there isn't. Okay, so let me just say it. What they want to do is they want to have they start with photons, they knit their photons into a state that is effectively a cluster state, but slightly different than a cluster state. Their only operation is a ZZ measurement, is a ZZ fusion measurement. So what they do is they take two of these photons and they measure them together and they correlate them. So their only operation is effectively taking two photons and fuse them into a single. They do the ZZ spider and they fuse it. I can just go onto the slides and show you what it is here. My hands are not doing it justice, I think. So that's the measurement they do. It's a bell basis measurement, and the effect is that they take pairs of qubits in their lattice and they fuse them together, and they can, if they fuse the right sites, they start with these hexagons and they obtain squares, and these squares are the squares of the cubic. They're just disjointed. They're just if you take a hexagon, you think of it, it's not a square, it's the face of a cube. Is sort of hexagonal, and that is their starting hexagon, and they fuse them to obtain something which is equivalent to the three-dimensional cluster state, and their computation turns out to be equivalent to 3D cluster state fault-tolerant quantum computing. So it's the same computational model, but with different basic operations. The logical state is the same, but the operation they use to obtain it is different. So the way that they don't perform the operations of the typical operations of MBQC, because those are too expensive, they just perform this fusion operation again and again on pairs of photons, and they hope to do it very efficiently and on large scale. So they say, if once we have these basic things set up, then we can just run it forever. We can keep our photons in like fiber optic lines and make them run around and knit them together by fusing. That's their plan, as far as publicly available. Now they're quite chatty about it. They used to not say much. Like, they used to say, we are working on stuff, but now they started publishing a bit more papers. But the technology itself is still secret, as far as I know.
But I mean, the question is that they connect all these different pieces where the temperature is an issue, or not an issue. That's the reason why I'm asking.
I have the exact specifics of the technology and how they want to perform this fusion. I don't think is known. And why would they publish it? I mean, they do truly believe that the moment they nail this, they can scale their optical computers arbitrarily. So they seem to be fairly tight-lipped about it. That doesn't mean that it works. It doesn't mean that it will work tomorrow. It may take a few years to work. Maybe it will never work. We don't know. It's like the optical switches, right? It's the holy grail of photonics, is having like a good, high quality optical switch. But maybe it is. I believe that these things can be. I believe they can be constructed. It's just an engineering problem. But I'd also feel I'd also feel very dismissive by saying it's an engineering problem, as if it was a simple thing. It's a very hard engineering problem. Moving stars is also an engineering problem. That doesn't mean it's easy.
Environment, temperature.
Yeah.
Those many of the things, there are penetration of
That's true.
That's wonderful.
But these are photons, so the hope is that as long as you have sufficiently high fidelity. Yeah, exactly. Yeah, exactly. From a fundamental physics perspective, photons are they're very cool. Yeah. They're highly decoupled from the environment.
So
I think we can stop.
Yeah. Tomorrow the plan was measurements to coherence, QKD.
So instead, tomorrow we do doubling probabilities and causality. Yeah. Yeah, it's the morning. And then in the afternoon, I'm going to talk maybe about some of this causality stuff, which is funky. So I'm going to stop sharing. Yeah, we have to stop now. Thank you. It was fun. Yes.
1019 or on Zoom. Thank you.